In this video, I want to talk about solving systems of linear inequalities. Example 1. We have y is greater than x minus 8 and y is less than 5 minus x. To simplify this problem, first let's rewrite the y is less than 5 minus x as negative x plus 5. We'll use two different colors. We'll use rainbow for the top one, and we'll use orange for the bottom one. So recall when we have a greater than or less than situation, we just use a dotted line. So first we have y is less than negative x minus 8. So we're going to find negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And plot the y-intercept. We're going to use our slope. And just make a dotted line. Now, since we're saying greater than negative, y is greater than, first we're going to find our solution shade. So we're going to use arrows this time. So we'll say 0 is greater than 0 minus 8. So we're still going to use that 0, 0 idea. So we're saying 0 is greater than negative 8, which is true. So we're going to draw arrows towards 0, 0. Now we're going to do the bottom equation. Y is less than negative x plus 5. So first find the y-intercept, 1, 2, 3, 4, 5. And then we use our slope, down 1 over 1. We'll just plot a few points on this line to make it easier to graph the line. So okay, again, we still have that 0, 0. So I'll do the work to this one on the right side. So we'll say 0 is less than 5 minus 0. So we're saying 0 is less than 5, and this is false. Oh, sorry, 0 is less than 5. That's true. So we're going to draw arrows going towards 0, 0. So the section we want to shade is where we see the rainbow arrows and the orange arrows. So let's break this into 4 regions. We have region 1, region 2, region 3, and region 4. You can see in region 2, there's only rainbow arrows, as the orange arrows are pointing away from region 2. In region 3, there's no arrows, and in region 4, there's only orange arrows. But if we look at region 1, we have the rainbow arrows coming in and the orange arrows coming in. So that's the section I want to shade, and I'm going to grab a highlighter and shade that. Let's shade it in blue. And once I'm done shading, I am done this problem. Okay, so region 1 is the region I want to shade, and I am done solving this system of inequalities. Example 2. We're given y is less than or equal to 2x plus 1, and y is greater than 2x minus 1. Just like in the last example, we'll do the top equation in rainbow, and we'll do the bottom equation in orange. So recall when we have a greater than or less than, this is a dashed line, And when we have a greater, less than or equal to or greater than or equal to, we want a solid line. So let's first graph the top. So we have a y-intercept of 1. We want to go up 2 over 1, up 2 over 1, up 2 over 1. So we have enough points that we can plot this line. Okay, I think we have enough points. And our line goes all the way to the end. So now we're going to use 0, 0. Because we can see that 0, 0 right here is not on the line. So we're going to say use 0, 0 again. So that's just saying 0 is less than or equal to 2 parentheses 0 plus 1. Or 0 is less than or equal to 1. That's true because 0 is less than 1. So we're going to draw arrows going towards 0, 0. Now we want to deal with the y is less than greater than 2x minus 1. So we graph the negative 1. And we're going to go up 1, up 2 over 1, up 2 over 1, up 2 over 1. And now we have our orange line. So we're saying 0 is greater than 2 parentheses 0 minus 1. 0 is greater than 2 times 0, 0 is greater than negative 1, which is true. So we want to draw arrows towards 0, 0. So we have a section in the middle between these two lines that we're going to shade. And that's the section, that's our solution, the area in between those two lines. And we're done. Example 3. Dominique has made a commitment to exercise in order to improve her fitness. Dominique would like to burn at least 2,000 calories per week through exercise, but wants to schedule at most 5 hours of exercise for each week. Dominique will be doing both walking and bike riding for exercise. Brisk walking burns about 400 calories per hour, and biking at a moderate pace burns 800 calories per hour. Write a system of linear inequalities that describes Dominique's exercise goals. So let's first define our, let's say walking is x. Oops. We'll say walking is x and bike riding is y. So let's also use our highlighter to get our important information. So anything that is for walking we'll highlight with a yellow marker. So she wants brisk walking burns 400 calories per hour. And we're also given that we'll use bike riding for green. Bike riding at a moderate pace burns 800 calories per hour. And we'll highlight in blue the maximum amount of calories would work. And we also will highlight in light blue how many hours you want to exercise. Which is 5 hours. So let's first deal with the calories. So we have 400. Sorry, that we got it backwards. Let's do y and x. We'll still use the same coloring scheme. Walking and bike riding. So walking will be on the y-axis, bike riding will be on the x. So we'll say 400 y plus 800x and at most she wants to burn at least 2,000 calories. So that will be greater than or equal to 2,000. So that handles our calories inequality. Now, she wants to exercise at most 5 hours each week. So we don't know how many bike riding hours or how many walking hours. So we'll just say y plus x is less than or equal to 5. And we'll continue highlighting, highlighting the x in green and the y in yellow. So now, before we go about identifying the points that work, let's first graph. So I graph y plus x is 5. So if we say we solve for our y-intercept, we just say y equals 5. And for our x-intercept, we say x is 5. So let's do that line in orange. We'll do this one in orange. Okay, then we're going to use this point 0, 0. To say 0 plus 0 is less than or equal to 5. 0 is less than or equal to 5, so we're going to draw arrows towards 0, 0. Now we have our 400y and 800x. So let's we're going to do that line in rainbow. So first we're going to divide, to get the y-intercept, we're going to do 2,000. So let's just do this work on the side. 400y is greater than or equal to 2,000. So we'll divide everything by 400. Get y is greater than or equal to 5. So we already have that plotted. So I'll just go over that. And then we're going to say 800x is greater than or equal to 2,000. So we'll divide everything by 800. So 2,000 divided by 800 is 2.5. So I'm going to say x is greater than or equal to 2.5. So on the x-axis, we're going to graph at 2.5. And again, if we plugged in, we're going to say, for this inequality, let's first connect them. So to shade it, you would say 400 times 0. So we use that 0, 0 idea. Plus 800 times 0 is greater or equal to 2,000. And 400 times 0 and 800 times 0 are both 0. So 0 plus 0 is 0. And 0 is greater than 2,000. This is false. So we're not going to shade towards 0, 0. This time we're going to shade away from 0, 0. So we're going to draw arrows going away from 0, 0. So now we're going to shade the section in between the two graphs. That's our solution region. So we've graphed it. We already handled part C. Now all we have to do is find some. All we have to do is find some points that work for part B. So it says for part B, it says identify at least 3 numbers of hours of walking, number of hours of walking, number of hours biking combinations that satisfy both Dominique's conditions. So we just have to pick some points that work. So for example, that point right there, that's in the solution region. So that'll be 3 biking hours, 1 walking hour. So 3, we'll use B for biking and 1 W for walking. So that's one option. Let's get a second option. Looks like 2 and 2. So we can do 2 and 2. So second option will be 2 biking hours. We'll use 2B and 2W for 2 biking hours, 2 walking hours. Let's try to find one more point. Okay, we can also do 3 biking hours and no walking. 3 biking hours and no walking. So our last option we could use, and we could always pick any other points that were in that shaded region, but we'll stop at 3 biking and 0 walking, and all these points would be within that solution region. I hope this helps you get a better understanding of solving problems with systems of inequalities.